Okay, so this is the second part of additional note 2, which is functional derivative. Now, recall we did already study some functional calculus. Rather, we studied integral calculus, integral functional calculus. By functional derivative, when we discuss this topic, what we are trying to do is to find the corresponding differential calculus. So functional differential calculus is what we are trying to develop and figure out how to do the calculations. So let us recall the basic features of the integral calculus that we already discussed earlier. So just like in ordinary calculus, we have an argument x, a point in the real line. Here, the argument in the functional case, the argument is not a point on the real line, rather an entire function. That is an argument. So in this case, argument is a typical physicist's language. More mathematically, more mathematically recognized language would be the domain. The domain is an entire function in an ordinary space, for example, in real line or something. So the argument is a function x of t, the entire function x of t. So that I should rather write it as so function x of t, which is also same as x within a square bracket. Now, what we did for the integral calculus, if you recall, so this is your time and this is your x, and we have an initial point and the final point and a function connecting these 2 points, and then we divided the entire time period from ti to tf into discrete values. So so t1, t2, t3, and so on. So the operational definition comes in the following manner, that a functional integral will be given in the following way. You divide the function by a set of divide the argument of the function t into a set of discrete values, and then for each value of discrete value of t, the value of the function, that is x of x at that value of t, can be treated as an independent variable. So x of tn can be written as xn. So at each discrete value of t, the value of x is an independent degree of freedom, and therefore a functional f of functional x is nothing but an ordinary function of all these xn's. So this, in this language, in the discrete version, it becomes an ordinary calculus, and then you can integrate each. When you integrate f, you can integrate over each xn's, and that's equivalent to the functional integral of fx. So so the functional integral fx is same as all these integrals, say okay, so a equal to 1 to n, or dxn, small n, and if of xn. Now, up to this point, it is okay, but this is not the end. This is more serious than this operation. And the additional seriousness comes from the precarious process of taking n going to infinity limit, which is basically reaching, approaching the continuum. So you have to take limit n goes to infinity in a particular manner, okay? And then you have to make sense of it. That is how you do. But the basic take-home message here is that there is a correspondence between this integral and the usual integrals in the discrete language. Usual integral, by which I mean that the integral that we usually do. So you can view this as a multivariate. So this is like a multivariate, multivariable integral calculus. So this is like multivariable integral calculus. Okay. And from that multivariable integral calculus, with certain continuum limit, you arrive at the functional. With certain continuum limit, you arrive at functional integral calculus. Okay, we will take the same approach for the functional differential calculus, where we do multivariable differential calculus and some type of continuum limit. We'll see what exactly that is, and we will come to the functional differential calculus. That is the approach, right? Now this is something we know. It is straightforward for us. So what we do is that the general calculations that we do on this side is basically del derivative with respect to xm1, derivative with respect to xm2, and so on, acting on this function and this can be calculated using a fundamental building block. So fundamental building block for this calculation is a result that del xm prime is nothing but Kronecker delta m comma m prime, because xm and xm prime are independent variables. That's what it is. Now this is very simple. But now when we come to on the functional side, functional differential calculus, what we have is that this continuum limit is not actually a limiting process, but it's a symbolic manipulation in this case, because we have to just recognize that this f is a function, just like this f is a function of x1, x2, xn, etc., x1, x2, and so on. This functional of x is a function of x t1, t2, but there is no difference between t1 and t2. These are continuum variables. Okay, so it is continuously distributed. So it is basically if I just write that in the continuous version of the same thing, then we will have derivative with respect to x of t1, derivative with respect to x of t2, and so on, acting on the functional x. So I'm using a different notation. Instead of partial, I'm using delta here, just to just to indicate that I'm talking about continuous argument, continuous variable indexes. So here we have discrete index, here we have continuous index. That's the only difference. Otherwise, it is. So then we should be writing the fundamental building block will be delta of xt divided by delta of xt prime, and that will be given by delta t minus t prime. Okay, it is just the continuum version of the Kronecker delta is the Dirac delta function. That's what we use here. Okay. Okay, so this is all I have to say about setting up the rules of calculation for functional derivatives, and all the other rules, just like in the discrete case, all the other rules like the usual way of calculating the derivatives should work. Okay, only change is that this is replaced by Dirac delta. Now let us now consider an example. And a result that we had assumed during the lecture. Let me do the calculation now. So show that delta s of x delta x of t is equal to minus t2 dt2 plus omega square of xt, where S is the harmonic oscillator action, is given by integral dt prime half m x dot t prime square minus m omega square x t prime square. Okay. I'll be calculating this. The goal is to calculate this functional derivative where S is given by this. Notice that in the integration I have used t prime. So just so there is no confusion between this variable and the variable appearing here. This is a derivative at a particular value, a derivative with respect to x at a particular value of t, while this t is integrated over. Now, in order to proceed with the calculation, we first define. So the way you do it is to define Carly E of x of t, x dot of t, and so on, in the following way, that if you calculate the variation of this action, then the result will be given by integral dt prime Carly E x of t prime x dot f t prime times delta x of t prime. Okay, so that is how you define Carly E, and if this is the expression, then delta s x delta x of t will be given by dt prime e x t prime x dot t prime and so on, delta x t prime delta x t. And since this is same as Dirac delta t minus t prime, you will get this result. So that was the motivation for defining E in that particular fashion here, in that particular fashion. Okay, so if we can calculate the variation and extract what E is, that must be same as this this quantity which we are trying to calculate. So the goal now here is to calculate E. So calculate E, for which you have to calculate the variation. you have integral dt prime half m. You have x dot square. When you take the variation, it's like x dot times x dot. So it will give you exactly the same way that happens in ordinary differentiation or ordinary variation. It is delta x times delta x dot times x dot plus x dot times delta x dot. So that gives you 2 times delta x dot t prime times x dot t prime minus half m omega square to delta x t prime x t prime. Now, so just let me make it a little clutter free. So this half and 2 cancel. So integral dt prime m times x dot t prime delta x dot t prime minus omega square x t prime delta x t prime. Now, what is this object? This is the time derivative. This is the variation of time derivative. Okay, so this is the variation of dx dt prime. But variation and time derivative are two independent operations. So it is same as dt dt prime of delta x of t prime. If you use that, then you have a time derivative here, and then you have this time derivative can be pulled outside, make a total time derivative minus the time derivative acting on this. That is how you can make delta x free of derivative. So there are two terms. One is the total time derivative of this, and the other minus, other one is minus one extra time derivative here, but delta x free. Now, first term, which is the total time derivative, is go to the boundary. So if you calculate this from A to B, which are the boundary points, your variation vanishes at these boundaries. So you take delta x at A is equal to delta x at B to be equal to 0. Okay, so then this total time derivative piece, that term becomes 0, and what you have is minus integral dt prime m x double dot t prime plus omega square x of t prime delta x of t prime, which implies that E x of t, x dot of t, and so on is nothing but minus m, okay, d2 dt2 plus omega square acting on xt, this term. Okay, and that's precisely what this result says. Okay, so combining this with this result and this result, you arrive at this result. Okay, so this is the one simple example of doing calculations involving functional derivative. That's the promised discussion. Let's see.